Now let us discuss another important application of operational amplifier, and that is that how we can use operational amplifier as in integrator. So let's draw the circuit for making use of this operational amplifier as an integrator. And in this case, what we do, we have an operational amplifier. Okay, so it has two inputs, and here we have a resistance Ri, and here we have the output of this operational amplifier, and this is the positive terminal and this is the negative terminal. And here we are going to use a capacitor in the feedback circuit of this operational amplifier. Now let us assume that the capacitance of this capacitor is CF, and let us ground the non-inverting terminal of this operational amplifier, and here we will subject the input signal to this operational amplifier. And here this is Vs, this is the voltage signal, and here we have a junction. Suppose this junction is junction P. And now let's analyze this circuit. This is an operational amplifier, and we have used a capacitor at the feedback point, and we have subjected the signal to the inverting terminal of the operational amplifier, and we have an output voltage V out, and this voltage is V1, and this here the voltage is V2. Now to move on, let us assume the current I is flowing here, and here I have IF, and here I have, say, IX, and we can immediately think about KCL. You can Kirchhoff's current law, and we can use that at the junction. We're using that at junction P. Okay, so what will be the outcome is the incoming current is I, and outgoing currents are IF and IX. Now, as we know that the input resistance resistance or impedance, you can say here, of operational amplifier, an ideal operational amplifier, is infinite. So if that's the case, we can think of Ohm's law, and we can realize that this Ix is zero for this situation. Now this equation will boil down to I. I is here, I equals IF. Here we have IF, right? So what we have, basically, we have Vs, we have V2, and then we have V out. Now let's write down this equation in terms of voltages and currents. So let me mark this page as page 1. And now what is expected here is that for I can write Vs minus V2. So this is Vs minus V2 upon Ri. Okay, this is equal to IF. Now IF is the current that we are subjecting to the capacitor, and I can write it mathematically as dqf upon dt. I think it should be clear up to this point. There should be no doubt. Now we can proceed on this Q. This is Vs minus V2 upon Ri. This is d upon dt of Q is Cf V. Now what is V in this case here? What is the potential difference? That is V2 minus V out. So here I'm going to write V2 minus V out. I think that should be clear. Now let's move on. What should I do now? I should use the concept of virtual ground. And what is the concept? The concept is simple, that V1 is 0, that means V2 should also be equal to 0. So this is because of virtual ground. Virtual ground. So if that's the case, I'm going to get Vs upon Ri equals d by dt of Cf v out. That to minus, and minus is obvious because we are subjecting the signal to the inverting terminal of the operational amplifier. So when this thing happens, now I can think of output that we will receive. This output will be it will be 1 upon Ri Cf negative Vs dt, right? Now if for the sake of mathematical simplicity, if I take this this V out as dV out, we can think of integrating this equation, and on integrating, what we are going to get is our V out it is minus 1 upon Ri Cf integral 0 to t Vs dt. So here things are clear that using an operational amplifier, we have actually been in a position to integrate this signal, that is Vs, and Vs was the input that was given to this operational amplifier. So what is V out? Basically, V out is the integration of Vs over the time t. So here we are able to understand that that how we can make use of an operational amplifier to act as an integrator, where a signal that's subjected to this operational amplifier can be integrated. Now the next important application of this operational amplifier is we can use it as differentiator. So operational amplifier as differentiator. So for this case, we can think of an operational amplifier like this, and having inputs, terminals like this, having an output V out. Now we will have our resistance, a feedback resistance here, and here we will make use of a capacitor, and then we will subject this capacitor to the input signal, and this is positive, this is negative, and here this is V1 and this is V2, this is RF, and the capacitance of this capacitor is CF, and let us assume that we have a current I, and this is I1, and this is IF, and we can use KCL here in the similar way as we did it in the previous case at some junction. Now this junction is junction P, junction P. So what we are going to get is this I is IF IF plus I1. That should be the case. And we better understand that that Zi is infinite, so I1 is 0, so I will be equal to IF. Right? I think it's clear up to this point. Now for I can write dq. Here it's not CF. Let's call it C here. Okay, so this is dq by dt instead of IF. IF is here. It is here. I can think of V2 minus V out. So this is come on. This is V2 upon V out upon RF. I think it should be clear up to this point. Now let's move on. Okay, so here we have now dq. Now I can write d by dt of CV. But what is V here? Yeah, what is V? Here V is, this is Vs minus V2. Okay, so this is Vs minus V2. Okay, this is equal to what? This is equal to yeah, what's that? This is V2 minus V out by RF. V2 minus V out by RF. Now we can use the concept of virtual ground here again, and in that case we know that V1 is equal to V2 is equal to 0. Because this V1 is grounded, so taking this at 0 potential, the potential at V1 must be equal to the potential at V2. So what's going to happen here is we're going to get d upon dt CVS, okay, that is 0, is equal to minus V out by RF. So what's the aim basically? The aim is basically to have the output from this operational amplifier, and that output should be a differentiated one. So I think the result is out here. So we can write down this V out is C RF. We can put a negative sign d upon dt of Vs. So we can see here in a similar situation that the output that we achieve from this operational amplifier will be the differentiation of the input signal Vs multiplied by some constants, and this negative sign is clear because it is the result, because the input that we are subjecting it to the inverting terminal. We are subjecting it to the negative terminal of the operational amplifier, and we understand that if we subject our signal to the negative terminal of the operational amplifier, it will change the polarity of that signal by 180 degree. So this negative sign is a result of that. So from this we are in a position to analyze that we can use an operational amplifier by virtue of which we can have the differentiation of a function, a differentiation of the signal that's subjected to this operational amplifier. So this way we have seen that operational amplifiers can be used as the summing apparatuses, and they can also be used as integrators, where we can integrate the input signals. They can also be used as differentiators, where an operational amplifier, by the help of the feedback can differentiate the input signal.